Thank you for having me tonight. My name is Jeffrey Ng, and I'm the CTO at Stratified Medical. So we haven't been doing too many meetups this year. Don't know if anybody has been to one of our previous talks. It may be some of the same slides, so apologies in advance. So my background, in a past life, I used to be an academic. As some of you here in the audience, I spent 7 years at Imperial College working on reverse engineering the human brain, in particular the human visual cortex. So after these 7 years, we had some mathematical models of how neurons behaved in the human brain, and we spun out the company to actually productize the code and put that in the cloud. So at the end, we raised quite a few £1 million in VC money, and we had these systems connected to the back ends of the likes of eBay, Macy's, working on recognizing images in real time in large databases. So I guess a lot of the tech that we see in London at the moment is coming from academia, it's coming from research, and this one as well. So enough about the old stuff. So now it's Stratified Medical, the new venture, and I'll tell you a little bit more about what we do. Just a quick pulse of the audience here. How many people in the audience has been taking a pill or other medication today? Can we have a raise of hands? Ooh, that's usually more than I usually have in the audience. Let's see next. How many people know somebody who has been seriously ill? So now we get more. So, health is something that touches every single one of us. But at the moment, there's a big gap between medical research and the healthcare that you get. So, as part of Stratified Medical, we're trying to close this gap, so to create better drugs, better medicine, through the use of deep learning. So it's exciting tech, but for a good purpose, for a good outcome. If you look at how much we're spending as a country on healthcare, so in 2015, the UK budget for the NHS was £116 billion. And of course, we don't get the care that we want. It's a lot of money, but still there's lots of inefficiencies. Where all that money, where is that all going? If you look at the pharma business, today it costs $10 billion to produce a new drug. And a large part of that cost is because of all the failures. If you look at the industry, about 95% to 97% of the compounds, the molecules that these guys design, don't make it to the counter. So there's very few industries today that can tolerate such a high failure rate, but it still happens. So we're trying to change all that. We're trying to change all that with tech, with AI, but this field is changing. So if you look at the Western world, the industrialized world, we're now living longer. So there are now diseases that evolution never saw, that it never developed a counter for, right? So there are novel medical needs. If you look at what they're doing in California, there's the Calico company by Google. So it's the California Life Company, where they're trying to extend lifespan. And it's a big field. It's 2015 today, and there's still very little that is known about the human body. And that's what I'm going to try to show you, where we are. So what's the cause of this failure rate? Why do drugs fail? So the first reason is usually efficacy. So they find a little molecule that does something on a cell in a petri dish, and then they put that in an animal or in a human, and it doesn't work. That's okay. But worse, it's toxicity. So who's heard about the latest problems they had in that drug trial in France where people died? Yeah, so that's because we don't know how the human body works, not really. And that's why the first time really where this thing works is when you put that, what we call first in human, and that's when things can go really wrong. So path to innovation, use tech to better understand human body. So we said a few people were taking pills. So who knows how drugs work? What do they do? We take them as a pill, it goes into our gut. What do they do? So how many in the audience know that we still don't know how paracetamol works? Right? If you go to Wikipedia and if you type drugs for which we don't know the mechanism, paracetamol is one of them. Right? We still take it. It still has an effect on us. It's a painkiller, but nobody's got a clue how that works. How can that be after all this time? If you look at that trend, it all started back from the Human Genome Project back in the year early part of the century, right? So back then, people thought if we could map the whole of the human genome, all the A, T, C's, and genes in our genetic code, we would understand how the human body works, and then we could cure all the illnesses that plague us. Everything will be solved. 15 years later, we're still not there. That's because the human, the genetic code only produces what's called, so DNA produces RNA, so that's one step, and RNA creates proteins. But these proteins actually interact like networks in the human body, and there's complex interactions that actually, at the end of those, result in controlling a body function, like your respiratory levels, your glucose levels in your body, etc., etc. So this is very complex. So I didn't answer the question, how do drugs work? So usually what they do is they bind to a protein in the body, and it's that protein that then has an effect on lowering your temperature or any other body function. If you look at this picture on the left here, so this is a tree of a particular type of protein called protein kinases. And the reason why we're interested in those is they operate on a lot of body functions. If you look at the color, the red ones are the ones that are the most active. So we have this holy trinity here. A drug compound would hit a target, and that would have an effect on the disease. So drug discovery is usually focused on finding new molecules that hit known targets, right? But if you keep hitting the same targets, you'll still keep having the same effect on the human body. What we're after is finding novel targets, understanding how the human body works to have a novel impact and a novel intervention point. So a lot of us now think it's not about finding, relying on serendipity to find new targets. Before, people used to look at medicinal plants, stuff that exists in nature that people found by chewing on a leaf or, something natural that had an effect on the body, and then they based their drugs on that. So now it's like, it's the age of the quantified self. We want to understand everything. So I think it's high time that we develop the tech to really know what these targets do, to really understand how our drugs work. So I was talking about these proteins that control the human body, and if anybody didn't believe me, how complex these things are. So this is a protein-protein interaction network. So the first proteins here actually interact with another protein, which interact with another protein, and this one is a bit promiscuous, right? It likes to, play with lots of other proteins, and then you get lots of more hubs like this. And at the end on the right, then you have the body function. So God knows how we've been able to create drug compounds that, from this input has an effect in there. And that's why, there are lots of side effects, what we call off-target effects. And unfortunately, that's why people still die during, human trials. So, this is post-genomics. So this is called interactomics. And there's a lot of research in trying to understand how this works. Right? But we're not starting from scratch. We have lots of knowledge of graph theory, network systems, distributed systems that we can apply to this big problem here. So how do the best drug scientists, how long does it need to train a good drug scientist? I won't ask the question because it's on the slide here. So it actually takes 40 years today to train a good drug scientist. It takes 40 years from the start of the training process for them to understand, this whole network or the human body. Ooh, who is this? So, yeah, 40 years, that's what it takes for somebody like, this great drug scientist here to understand all that inside their brain. But if you think about it, this is a typical data silo. This person takes 40 years to learn all of that, and then what happens at the end? It's almost time to retire, right? You lose all that expertise. Or, in the middle, they might change jobs. The big drug companies might decide to close their labs, as is happening here in the UK. You might decide, it's a change of lifestyle, whatever. So you lose all that knowledge. Has people seen this article where Google has been networking their robotic arms, right? It's like they have about 40, it's like a whole factory. But if one learns how to better grasp an object, because this is all centralized, they all learn this, right? So all the arms can learn that. So I think this is the age where machines will be learning, and then they don't go away after 40 years, right? So hopefully we'll be building systems that will be with us for thousands of years, where that knowledge can keep being applied. And I know some of you are saying this is sci-fi at the moment, but maybe some of the future slides will show you some of the advances we're doing in AI and deep learning. So this is what we do here at Stratified. You have on the left, so you have lots of structured databases. We have millions of entities that people have curated, 10 times more that in terms of relationships, so what one does to the other. But where does all that data come from? All that data is being curated from publications in Nature, in the British Medical Journal, in The Lancet. So that's where people are being very active, researching all that, doing lots of experiments, high throughput experiments, next generation genome sequencing, molecular phenotypic experiments. So all that's being published. And you're relying on a few academic teams across the world to read the paper and put that in a structured database. So like in the RDF data format, right? You have entity A has a predicate that links it to entity B, and that's all they're doing. But as you may know, the data is doubling every 2 or 3 years. So already these human curators can't keep up with the amount of scientific publications going out there, right? How are we going to move on as a system? So, ta-da, Q, it's with artificial systems. So there's lots of NLP effort going into getting machines to read these scientific articles, extract all the knowledge, and then put that into a big knowledge graph. And this is, what we have as our platform at Stratified Medical. So it takes in structured knowledge, it takes in unstructured text, processes all of that. So we have a cluster of machines in the cloud now that can process 30 million articles in a couple of hours. So, there's some of human knowledge, and this is good knowledge from nature, science, neuron, etc. All being catalogued, linked. We're mapping out what each one does, how they interact with each other, with a view to actually helping that drug scientist. You don't need to train somebody for 40 years. You can train something in a couple of days, and they can already help by narrowing down on this whole scope of data in here, right? Of course, we're not going to replicate a human in 2 or 3 days. It's not our intention. It's not about replacing the human, but it's about augmenting the human with systems that does all the lazy work, right? All the laborious work, which is reading the papers and keeping up with the literature. So now the human can actually be freed to do what they do best, which is invent, connect data, invent. So be innovative, be creative, and actually find where we can, where we can intervene with a new drug. So I can't tell you exactly, I think that's maybe a difference of my talk with some of the others coming here. I can't tell you exactly how we do things, but I can give you a few experiments, a few results that gives you a flavor of what these systems do. So this is a framework that I've thought is very helpful in terms of thinking about these systems. So you have a document that's just come in, right? It's from Nature. So we look at the provenance. So we look at the impact factor of the journal. We look at the authors, whether they're well cited, what other works they've published, And that all tells our system how much weight to put to that whole document. Once the document's that's come in, we do the language modeling. So that's all the natural language processing, that's all the named entity recognition, finding all the diseases, the chemicals, the proteins in the paper, and then extracting all the surface form variations. So how many NLP people do we have in the audience? All right. So you will understand what surface form variations mean. But let's take, for example, a professor, an esteemed professor, has published in Nature that, say, a new molecule, 103D5R, inhibits tumor necrosis factor alpha. Right? So we know that tumor necrosis factor alpha has the effect of that is inflammation in the human body. Somebody else, another professor, might actually write that it has been discovered this molecule has an effect on TNF, right? Others might say it has been found that this molecule in TNF causes inflammation in the liver, etc., etc. So there are different ways to express the same meaning with different levels of subtlety. And you actually need your system to cope with all these variations in the language and the verbs used, in the way that you use past tense, present tense, etc. So what happens when you've dealt with the language? Then you're left with knowledge. So how do you model these big networks? In here. So this is very domain dependent. So we had to build a whole knowledge graph, or knowledge space, as we call it, to encode the core entities that's of relevance to us and the impact that they have on each other. Okay, so if you've done this, you say, great, we've got a system that can read nature, right? Can we do anything with it? So now our genius scientist comes in, right, sits down in front of the computer, this big system that we call JAX, and then puts a query. So he's going to ask, I'm looking at Alzheimer's today. What protein targets are involved in Alzheimer's and why? So this is the knowledge reasoning part. So the system must know what he actually means by that question. So take, for example, if he had asked for a drug for Alzheimer's, some of the most common elements in the human body is nickel. So the system will go to the knowledge graph and say, nickel is present in both. Is that a good answer? If you give that to the scientists, they're probably saying, that's the most common element. Why wouldn't that, why in the hell would you give that to me? It's of no consequence, or of no information. So the system must know what the user means, reflect on that, and then give an answer. And even then, if you had a system that just said, the molecule that I mentioned before, 103D5R, is your answer, who can guess what's going to be, what the user is going to say, or how the user is going to react? It's a bit like saying, what's the answer to life? And we say 42. Right? So he's going to say, this is a machine, it's a black box. You give me an answer, it's 103D5R. Explain to me why you've shown that. Explain to me why this is relevant. And that's when the system needs the smarts to go into both its knowledge model and its language model to explain what are the links it has found. It has found this little nugget here in nature. It has found this other little nugget in BMJ, put the two together, and that's why it's giving the answer to the scientist. But this is the knowledge reasoning framework that we're trying to propose. And of course, I talked about document parsing, etc., so unstructured text, but you also have to link that with your structured databases, your knowledge graphs, your knowledge, etc. Okay, so enough about reasoning. Let's talk about deep neural networks, because that's very much in vogue at the moment. Very cool. So this is a particular NLP task. So we've built a network. You've got a little sentence here saying, consequently, these results suggest that physiologically relevant concentrations of ethanol may affect production of inflammatory cytokines, such as tumor necrosis factor alpha. Right? So what we want is the system to actually say, text goes in, give us the goods, give us the entities, so the subject is ethanol, The predicate here is gene expression, is expressing something, and the object is tumor necrosis factor alpha. Right? So it's given you the essence that you can build your knowledge graph with that. Ethanol, by the way, is the stuff that we have on the table there. And this is what it's going to do with the liver. It's going to inflame your liver. So I'm not putting you off the booze at all afterwards. But this is a data science meetup. So if you look at the state of the art in NLP for this type of information extraction, which is on the left here, and you look at a deep neural network that we've trained to do that, this particular one here, we have a 15% increase in accuracy straight off without playing too much with the DNN, without creating very deep layers, great architecture. So this is what the approach gives you out of the box. So now our engineers are very curious by nature. So not content with extracting information. They said, well, we're very curious. So for those who know how neural networks work, they store internal states inside the network. So here you have these states that change after every single word has been input into the system. So our engineers asked, what's this thing actually storing inside? Yeah, we see the output coming out, but it's like, what do androids dream of? And, it's electric sheep. But, is it really electric sheep here? So we built further layers or further steps that actually try to recreate the original sentence, right? So what has it learned, right? Before we can start to trust these things, if they're going to tell us, put this molecule into the human body. So, yeah, we're trying to reconstruct it. So the next bit is a set of 3 input-outputs that we put into the system. So first one has been reconstructed perfectly, 100%. So we know we've lost nothing. Right? The internal network, the internal state of the network is the same as what's gone in. If you look at the second, the only change here is where the system got as input modifies, but then it stored effects. So it's still in keeping with the meaning of the sentence. It's at the last one where it gets a bit more hairy, where our engineers were scratching their heads. DNA breaks is the same as DNA damage. That's not a big problem. But the last bit says is required for cell survival. That's pretty important, isn't it? The other one is promote cell survival at the membrane. So, our scientists are digging into, the understanding of that and what it means for the systems that we're building and how much we can rely, what's the reliability of these systems in predicting new knowledge, etc. So here, the system could either be hallucinating, right? Or because of all its knowledge, because remember, this network has been trained on the whole of Nature and Neuron and all the scientific articles. Maybe it's expressing a novel view of the data, something that, wasn't apparent. It's putting 2 and 2 together. And that's still ongoing into, we're digging into these things. So the last bit is probably where it gets, that's another use case. So you have a knowledge base, we're all used to Wikipedia, DVpedia, and all that. And then you have lots of text, 30 million publications. Our engineers asked, can we actually train a system that, given this, and no knowledge at all? So maybe some basic NLP here, right? So it knows what the named entities are, etc. But just with the named entities, with a knowledge base, can it learn to read? Right? Given that it knows this thing is saying there are connections between 2 types of entities, and you've got a long list of these. Now it's going to look at all the surface form variations, all these encodings into the deep neural networks, and it's going to start to learn to associate which surface form variations here are linked to these connections that we care so deeply about. So this is really a network. It's not a supervised task that you usually do, because in the supervised learning sense, you actually give it very detailed annotations of everything you want to extract. So this is not this case. This is, broadly speaking, we know this thing is related to that other thing. Go and find out, go and learn how to read. Oh, that's gone. Strange. Go and learn how to read that from text. And this is the next example. So here it's connections between disease and protein targets that the system has retrieved for us. So it ranked these two very high, and this is very low. So here it's saying mutations in this gene have been reported as a cause of Alzheimer's disease. So it is finally, this is one of the top ranking sentences. So it has learned that this sentence, the surface form variation, is an important link or a mention of an important link in your text between these two entities. Here the second as well, so it's here saying the gene, cholesterol 27 hydroxylase was recently identified as a susceptibility for Alzheimer's disease. Then the next one that is rated much lower is the role of calpain in early. So you can see that what it rates highly shows a good link between the two entities, and what it ranks lowly is something that is a bit more speculative. In this case, it was a model in the paper that showed this role. These are great advances in machine learning. Of course, I can't tell you exactly all of our latest results. That will come out in time. But you've got systems that, given knowledge bases, are starting to learn to read text and understand text. And we've already got results that go beyond that. So once you can read and understand, or the system can read and understand, how can you reason on that? So how can you start to predict connections based on all the knowledge that you have? And this is what we're trying to solve here at Stratified Medical. So a bit on how you do that practically, since it is an applied meetup. So we use GPUs, graphics processing units. So a long time ago, these things used to be done on CPUs, and that was in the 80s. A long time ago when neural networks couldn't scale. So a lot of us have been saying the same thing. So the main reason for the revival in deep neural networks, or neural networks in general, is one, we have more data, and two, we have more processing power. All right. So you will have the evangelists that will be talking about dropout, about all these algorithmic tricks that they do to get their networks to perform better. But I still think the biggest component is these two, data and compute. Right? And it's mainly these GPUs that have allowed us to actually train these bigger networks. And it's not rocket science either. So what we do when we train neural networks is we try to reduce an error. And the way to do that is we propagate the error gradient back from the final result all the way to the input signals. And so it self-corrects as it goes through the different layers of the network. And these computations, these are matrix-like operators using BLAST-type algorithms, are easily done by GPUs because that's the bread and butter. If you think back about the good old days when GPUs were used for graphics, they were taking projection matrices, so they were taking matrices operating on vectors to put things on your screen. And now we're just doing different things with them. So it's the same circuitry, but they're training the internal weights of the neural network to allow you to train or to obtain a better function approximator or function predictor. So here, this is an example where if CPU is 1x, you use a GPU, you get an 11x speed up. You use the manufacturer-supplied libraries, and you get a 14x. So that's the difference between 14 days and 1 day. And we all know in data science, these short cycles are always the best because you need to iterate very quickly. So that means, that's the difference between life and death in terms of a data scientist. So I hope I've shown you today that there is an opportunity to apply AI and big data to something that's very important to all of us, as a society, in terms of finding drugs to target disease. We're trying to adopt an explanatory approach, so taking a lot of nature and all the scientific articles to understand and to explain to the user, all that knowledge. And deep learning has been, working great for us. So connecting these nuggets with AI, we think, is the future. And although we're applying these to the drug aspect, because this is the vertical that we're in, you can imagine this technology being applied to any area of human knowledge, as long as you have the publications and you have some start of a knowledge graph, a knowledge base. Great. Thank you.